Hello everyone, myself Chakshu. In this video, we'll learn about voltage to current converter. The contents of this video are introduction to voltage to current converter, an operational amplifier which is also known as op-amp, floating load voltage to current converter using op-amp, ground load voltage to current converter using op-amp, and the applications of voltage to current converters. Firstly, we'll learn about voltage to current converter. A voltage to current converter, also known as V2I converter, is an electronic circuit that takes voltage as the input and produces current as the output. As we can see in this figure over here, the voltage is taken as the input and we get current as the output. This is the use of a voltage to current converter. Voltage to current converter. The circuit diagram of a resistor which performs as a simple voltage to current converter is represented beside. In this diagram, the electrical quantities such as voltage and current are represented through bars and loop respectively. But practically, the output of this converter depends directly on the voltage across the connected load in addition to the input voltage. Therefore, VR becomes Vin minus VL. Before going deep into this video, first we'll learn about Ohm's law. Ohm's law states that the voltage across a conductor is directly proportional to the current flowing through it, provided all the physical conditions and the temperature remains constant. Operational amplifier. It is also known as op-amp. They are one of the basic building blocks of analog electronic circuits. Operational amplifiers are linear devices that have all properties required for DC amplification and are used extensively in signal conditioning, filtering, or to perform mathematical operations such as addition, subtraction, integration, and differentiation. An operational amplifier is a three-terminal device which consists of two high impedance inputs. One of the inputs is called as inverting input, marked with a negative or minus sign. The other input is called as non-inverting input, marked with a positive or a plus sign. A third terminal is the output port, which can both sink and source either a voltage or a current. The following details are given in the diagram. An op-amp is implemented to simply convert the voltage signal to a corresponding current signal. The op-amp used for this purpose is IC LM741. This op-amp is designed to hold a precise amount of current by applying the voltage which is essential to sustain the current throughout the circuit. There are two types of op-amps. One is inverting op-amp, another one is non-inverting op-amp. In an inverting op-amp, the amplifier gain, that is A, is given by V out by V in is equal to minus Rf by Rn. Whereas in a non-inverting op-amp, A is given by V out by V in is equal to 1 plus Rf by Rn. In this slide, let us take a look at the differences between an inverting amplifier and a non-inverting amplifier. First, let us look at the basics. In an inverting amplifier, it provides a amplified signal which is out of phase with the applied input, whereas in a non-inverting amplifier, it provides an amplified signal which is in phase with the signal present at the input. Next, we'll see the phase difference between the input and the output. In an inverting amplifier, the phase difference between an input and the output is 180 degree, whereas in a non-inverting amplifier, the phase difference between the input and the output is 0 degree. In an inverting amplifier, the input is applied at the negative input terminal, whereas in a non-inverting amplifier, the input is applied at the positive input terminal. The achieved output in an inverting amplifier is inverted in nature, whereas the achieved input in a non-inverting amplifier is non-inverted in nature. In an inverting amplifier, it is expressed as negative polarity, whereas in a non-inverting amplifier, it is expressed as positive polarity. In an inverting amplifier, the positive input terminal is grounded, whereas in the non-inverting amplifier, the negative terminal is grounded. The gain polarity in an inverting amplifier is negative, whereas the gain polarity in a non-inverting amplifier is positive. The gain of the amplifier in an inverting amplifier is that is A is equal to V out by Vn is equal to minus Rf by Rn. Whereas in a non-inverting amplifier, the gain of amplifier is equal to V out by Vn is equal to 1 plus Rf by Rn. We can convert voltage to current in two ways. One is using passive circuit components and the other one is using active circuit components such as op amps. Now let us see how to design it using passive circuit components. So here, just by connecting the resistor in series with the voltage source, we can convert the voltage into current, and the relation is given by I is equal to V in by R. This relation is obtained by applying Ohm's law. Now, if we connect the load resistor in series with the input resistance, the current I should also flow through the resistor here, because we are assuming that there is no voltage drop across the load resistor. But actually, there is some voltage drop across this load, and because of that, the current flowing through the load will also change. In this given equation, we can know that I1 is equal to V in by R plus RL. Floating load voltage to current converter. As the name indicates, the load resistor is floating in this converter circuit. That is, the resistor RL is not linked to the ground. The voltage Vn, which is the input voltage, is given to the non-inverting input terminal. The inverting input terminal is driven by the feedback voltage, which is across the RL resistor. First, we'll learn what is KCL. KCL stands for Kirchhoff's current law. The algebraic sum of the current entering a node must be equal to the current algebraic sum of the current leaving the node. By applying KCL to this circuit, we get I is equal to IL. From Ohm's law, we know that current is equal to voltage by resistance. Therefore, V in by R is equal to I. Next, we know that I is equal to IL. Therefore, IL is equal to V in by R. Ground load voltage to current converter. This V2I converter is also known as Howland current converter. Here, one end of the load is always grounded. The V2I converter with ground load is as shown in the figure. Now, we have to apply KCL to the given circuit. Before doing that, let us know what KCL is. KCL stands for Kirchhoff's current law. It states that the algebraic sum of all currents entering and exiting a node must equal to 0. By applying the KCL to given circuit at point A, we get I1 plus I2 is equal to IL. That is, the algebraic sum of the currents entering a node is equal to the algebraic sum of the currents leaving the node. By Ohm's law, we know that current can be written as voltage by resistance. Therefore, here I1 can be written as Vin minus V1 by R, and I2 can be written as V0 minus V1 by R. By solving this further, that is by taking LCM and sending R to the other side, we get Vin plus V0 minus 2V1 is equal to IL into R. Let us keep this equation aside for the current moment, and let us concentrate on the amplification gain. As I told earlier, the amplification gain for a non-inverting amplifier is V0 by Vin is equal to 1 plus RF by Rin. Uh, that is what is given over here. We have just shifted the V into the other side to get the output voltage. V0 is the output voltage over here. Therefore, V0 is equal to 1 plus RF by R1 into V plus. Here, the voltage at the in non-inverting terminal is V1. Therefore, it can be written as V0 is equal to 1 plus R by R into V1. Here, the resistance of the feedback resistor is R, and the resistance of the input resistor is R. This can be solved further to get V0 is equal to 2V1. By using this equation in the other equation, we get Vn plus 2V1 minus 2V1 is equal to IL into R. By solving this further, we get Vn is equal to IL into R, or IL is equal to Vn by R. Now let us take a look at the applications of voltage to current converters. There are many applications of voltage to current converters. A few of them are low AC and DC voltmeters, testing LEDs, testing diodes, it may be Zener diode, driving the LEDs, and the last application is to convert the sensor voltage into current in industrial applications. In this slide, we'll learn about one of the applications of voltage to current converters, that is, to convert the sensor voltage into current in industrial applications. There is a sensor which is used in industries. It might be a pressure sensor or a temperature sensor or any other sensor. If you have to send voltage from the sensor unit to a display unit which is quite at a distance from the sensor unit, then there will be a voltage drop in between. Uh, the same is shown in the graph below. As the distance increases, the voltage keeps decreasing. To overcome this problem, we use a voltage to current converter in between the sensor and the display unit. Now, if we have to send the voltage from sensor unit to a display unit, which is quite at a distance from the sensor unit, we add a voltage to current converter in middle. Then uh, we convert the voltage into current in the converter, then pass the current from the converter to the display unit. So we know that the current remains the same irrespective of the distance. Therefore, the current remains the same as the distance increases. That is given in the graph below. Now we shall learn about another application of voltage to current converter. Ground load voltage to current converter is used to drive the diodes such as LEDs and Zener diodes. Once we set the value of resistor R and the input voltage Vin, then the current flowing through this LED will be constant. If we change the value of the input voltage, then the current flowing through that LED will also change. And we can use this circuit to test the brightness of the different LEDs for constant current. Similarly, this type of converter is useful in finding the matched pair of diodes and Zener diodes. Zener diodes are special purpose diodes. They are heavily doped. They are operated in reverse bias condition. One of its main application is voltage regulators. If we connect the Zener diode as shown in the figure, then the output voltage will be Vin plus Vz. So while measuring the output voltage at the output terminal, we can find the two exact matched pairs of Zener diodes which has the same value of this Vz. This is one of the applications of voltage to current converter. That brings us to the end of this video. Thank you everyone.